So we're going to finish up the notes we started yesterday. We started with isotopes. We talked about what they are, gave some examples of carbon-12, carbon-14, where it's really the same atom, but it's an atom that has different numbers of neutrons. So sometimes carbon will have the equal number of protons and neutrons and give it atomic mass of 12. But then sometimes it has a couple extra neutrons and it gives it atomic mass of 14. So whenever you see an element name and a number after it, this tells you the atomic mass, and that's just protons plus neutrons, and that's in your notes. You can check that out. So we have all these different, these are called isotopes, lots of these different ones that have different numbers of neutrons and protons. And if you remember, we also said that the lighter elements, the ones at the top of the periodic table, tend to have equal numbers of protons and neutrons. But as you move down further and further, especially into the bottom layer, you get to rare earth, lanthanides, and actinides, and they tend to have much more neutrons and protons, and that makes them unstable, and they tend to give off those neutrons to try to get even, and they become radioactive. Okay, and we use those kind of isotopes for different things, like smoke detectors. Everybody probably has that in their house. They use, if you've ever gotten an MRI, they have you drink it, and then it helps them locate certain things in your body and take a good picture of it. And then they also use it to treat food, and then for dating of organisms. Every living thing is made up of carbon, and we have parts of carbon-12 and 14. When you're walking around on the earth, you have a set amount, but then when you die, that carbon-14 starts changing into carbon-12, and they can tell, if they get a skeleton, how much carbon-14 is left, how long ago that organism died. Okay. The thing we didn't cover was something called average atomic mass, and we're going to kind of cover that today. I'm going to show you how to do these problems, and then you're going to practice some in class. Okay. So the average atomic mass, and if you remember on the periodic table, so in the periodic table you have all these different things it tells you about, like the whole numbers, or see if I can get really close here. So you see the OS osmium, you have this 76 right here. Where is it? Right here. And that's your atomic number. That tells you how many protons it has. Then it has this number down here, 190.23. And that is the average atomic mass. Okay. The average atomic mass is related to isotopes. So if everything was even, like carbon had 6 protons and 6 neutrons, the average atomic mass, if it was always the same, would be 12. But we don't have that. Some elements have all these different isotopes, and so we have to add them all together and figure out what the average atomic mass is. Because that's how you figure out atomic mass. It's how many protons and neutrons. And whenever they list the atomic mass, let me go back out here. So whenever they list atomic mass, that's in a unit called the AMU, or atomic mass unit. So that's a number they use in chemistry. So like they have different units for things. You buy meat by the pound, you buy gas by the gallon. Well, we count elements, or weigh them, by atomic mass units. Okay. Elements, or elements, as you know, they occur in different proportions. So like if we had carbon-12 and carbon-14, those are the two isotopes for carbon. They have a certain natural abundance, or how much they are normally found. How much is normally found? Okay. How much is normally found of each? So it's usually going to be a percentage. So maybe if we looked in the atmosphere, there might be 75% carbon-12 and 25% carbon-14. And then they can use these percentages and these masses to figure out what is the average atomic mass for an element. The equation you use is the fraction of the percentage times the mass, and then for each isotope you do the same thing, the fraction of the percentage times the mass, and you just keep adding whatever that total would be. So if we did carbon, let's just say it was 75 and 25. If we did carbon, we would see the fraction of the percentage would be 75 out of 100. We would times that by the mass of carbon. If this was carbon 12, we would say it's 12. And then we take the next one, carbon 14, we'd say 25 over 100, and we would times by 14. And if we had another one, we'd keep adding it. But here we don't have that. And then we would just do the math. So if I was going to do the math for this one, I would just take 75 divided by 100, and then I times that by 12, and that would give me 9. Then I would add to the other one, 25 divided by 100 times 14, give me 3.5. And then I would just add those two together, and I would get 12.5. And if these were the right percentages, that would give me 12.5 AMU. I'm not sure exactly. Let me look in the periodic table, see what carbon is. I kind of made the numbers up, and it is 12.01. So there's a different percentage here than what I'm showing. But this is how you do it. You just take whatever the fraction of the percentage is times that atomic mass it gives you, and then you just keep however many isotopes you have, you just keep adding them together. Now I'm going to show you an example problem. You have a worksheet to do on these. Let me just review though really quick. So average atomic mass is the average from all the different masses of each isotope. So if you remember here, we had carbon 12 and 14. We take their masses and we include in this the percentage of natural abundance, and you're going to have to be given that. That's not something you can just know. It's just something you have to know. And then you're just going to plug it into this equation right here. And I'm going to give you an example here in just a minute. And then you get, in the end, you get a 9. Whole numbers are pretty close to it, and you're going to get a whole number. And what's really cool about this, you can check it on the periodic table. So let's go ahead and look at an example problem. This will be the first one on your worksheet. Okay, so let's look at this first one, and you can check your answers when you're ready. You can add this onto your paper if you want as we're going. That might actually be helpful, but let me just show you this one, first one. Then you can do 2, 3, and 4. They're really the same kind of problem. So it says the element copper has naturally occurring isotopes with the numbers. So this is going to be your mass numbers 63 and 65. Okay, and then it gives you the relative abundance and atomic masses. So the relative abundance are 69.2. And it's going to give you not that mass of like 63, it's going to give you much more defined 62.93. And it's going to have a 30.8%, and that's going to give you a mass of 64.93. So 69.2% for this mass and 30.8% for this mass. So we're going to use that thing where we just do the percentage times the mass, and then add each one of those isotopes as we go. So if we start off with this one first, we're going to go 69.2 divided by 100. We're going to times that by 62.93. Then we're going to add the next isotope, which is going to be 30.8, divide that by 100, and then we're going to times it by 64.93. Then we're going to do the math, okay, each one at a time. So I'm just going to take, I'm going to show you the work here. I'm going to do 69.2, I'm going to divide by 100, and then I'm going to times it by 62.93. It's going to give me this big number. It's going to be 43.54, and I'm going to write it, 54756. And I'm going to add that to the next one. Do the math, put it over here, and then I'm going to do 30.8 divided by 100. It's going to give me that. Then I'm going to times it by 64.93. And that's going to give me 19.99844. Now, you might say, whoa, those are some big numbers, and I don't want to really add them together with all those decimals, and you don't really have to. What you want to do is you want to look at your problem that you just did, and this is called something called significant figures. I'm just going to go over it really quick here. So we look at the least accurate of your numbers that you used. The 100 is very accurate. That one doesn't count. The 69.2, we have 1 decimal here. We have 2 decimals. We take the less one. So our answer then needs to be 1 decimal. So this one has 1, so we look at 43.5. Then we see if we round up or down, it's 5.4. 4 next to it, so we're just going to keep that, 43.5. Then we look at the next one. This has, we don't care about the 100. We look at the 30.8, and this one has 2, this one has 1, so this one's going to have 1. Okay. We look at this number, 9. It has a 9 next to it, so we're going to round up, and this becomes 20.0. And we add them 43.5 plus 20.0. It's going to be 63.5. And then the unit is AMU. So that should be the average atomic mass of copper. If we then get our periodic table and look at it and see if we're close. It might not be exactly, because they might use some more accurate numbers here, but it should be close. If we look at copper, we see it's 63.546. And we have 63.5. It's perfect. So that's how you do those. You should try 2, 3, and 4 now. Turn that in. I've also given the answers to Mr. Smither, and I have them hanging in my classroom as well. I just want to show you something though on question 3. Okay, it doesn't give you the atomic mass. So on 3, let's see if I can go out a little bit here to get this straight. So on this one, it gives you the number of protons and neutrons. So you just need to add them. So 82 plus 122. Math. I used to be able to do this stuff in my head pretty easy. As I get older, it's not so easy. So you want to just do it. 82 plus 122. That would be 204. So that would be our atomic mass. And then we'd multiply it by this, 1.37 over 100. Do that for each one and calculate. Okay. And then when you're done, you can then look at your periodic table and see which one, or see if it matches to the element. And this one is lead. It's going to be Pb. And then look at the periodic table. They should be pretty close. So that's kind of the notes. Mr. Smither and I have them hanging in my classroom. The answers to all these, if you do them and want to look back and make sure you did them right. And if you're still having trouble, you can do your best and then see me in class, and we'll go over some of these as well. But I think this will work for you. Let me know if you have any questions.